This video describes a new procedure added to Statgraphics 18 for fitting classification and regression trees. Part 1 of the video describes classification trees. Part 2 deals with regression trees. Fitting classification and regression trees is a machine learning process for predicting observations based on data. There are two kinds of models: classification models that divide observations into groups, and regression models that predict the value of a quantitative variable. The procedure creates a tree, each node of which represents a binary decision. We travel down the branches of the tree until a terminating leaf is located. That leaf is associated with a predicted class or value. Statgraphics 18 interfaces with the tree package in R, which runs the algorithm and returns the tree. As an example, you see here data describing 178 bottles of wine. The wine is divided into 3 classes according to where the bottle was produced. 13 measurements have been made on the wine in each of the bottles. Our desire is to create an algorithm that, using this type of data, can correctly classify where additional bottles were produced. What the procedure is going to do for us is create a decision tree. If we wish to classify a bottle of wine, we'll start at the top of the tree. If the flavonoids are less than 1.575, we'll travel along the left branch and then look at the color intensity. If the color intensity is less than 3.825, we'll classify the bottle as belonging to class 2. If color intensity is greater or equal to 3.825, we'll classify it as class 3. If the flavonoids are not less than 1.575, we'll travel along the right branch of the tree. We'll then look at the prolines. If they're less than 724.5, it's class 2. Otherwise, we look at the color intensity. If that's less than 3.55, we'll pick class 2. Otherwise, we'll predict class 1. The trick, of course, is to develop a tree with the right level of complexity. We want it to pick enough of those 13 variables to correctly classify the wine. But we don't want to build a decision tree that's so complicated that it can't predict additional bottles. In order to fit classification and regression trees, the first thing you'll need to do is install R on your computer. To install R, go to R interface on the main Statgraphics menu. This will open up the dialog box you see here. Press Install and follow the instructions to install R on your computer. Once that's done, you'll also need to install several packages. In particular, you'll need to install Pandoc, R Markdown, RCPP, String I, and ggplot2. Finally, you'll need to press the Install Tree button here to install the procedure that actually fits the classification and regression trees. There's a separate video on installing R if you have any problems. Once R and the tree package are installed, you can then go to the main Statgraphics 18 menu and select R Interface, Classification and Regression Trees. This dialog box will then be displayed. On it, you begin by specifying the dependent variable. If you're fitting a classification tree, the dependent variable is the column that contains identifiers of the class each row in your data file belongs to. You can then enter names of categorical factors or quantitative factors or a combination of the two. In this case, I have 13 quantitative predictors that I'd like to be considered for inclusion in the tree. The procedure builds the tree beginning at the top. It takes all of the observations, in this case our 178 bottles of wine. It then looks through all of the possible predictor variables to find a binary decision which will best divide those bottles of wine into two groups. It creates two branches based upon that binary decision, and at the end of each of those branches considers placing an additional node based upon another binary decision. We can control how complicated the tree gets by setting certain options in the partitioning section of this dialog box. As you can see, there are three options that we can set. The first option is the smallest allowed node size. Right now, it tells the program not to add a binary decision to a node unless there are at least 10 observations that have moved through the tree and are located at that node. We can also tell it the minimum observations allowed in each of the children if in fact it breaks the node apart and creates two branches. By default, we won't let it split a node unless there'll be at least 5 observations on both the left and the right. We also can restrict the splitting of nodes by specifying the minimum within node deviance to be allowed to split a node. In order to understand how it decides which variable to use to partition a node, you need to understand a concept called deviance. I'm going to introduce here a little notation. I'm going to start off by letting n be the number of observations in the training set. The training set is the set of rows used to develop the decision tree. In many cases, that's all of the data, although sometimes a certain section of rows are withheld for validation. I'm going to let m be the number of classes. It's 3 for the wine data. I'm going to let k be the number of terminating leaves. That's the number of end branches in my tree. N sub I will represent the number of observations that make it to node I. A node is a place where there's either a split or a terminating node. That would be a leaf. I'm also going to let n sub ij be the number of observations that make it to node I and also belong to class J. The deviance at node I is -2 times the summation across the classes of n sub ij times the log of p hat sub ij, where p hat sub ij is the fraction of the observations that make it to node I and also belong to class J. This is related to the log likelihood function of a multinomial distribution at node I. Basically, the smaller the deviance at a particular node, the more reliable the prediction. It's also common to talk about the residual mean deviance. The residual mean deviance is the summation of the deviance across all of the terminating leaves divided by the number of observations minus the number of leaves. In deciding how to split a node, the program will look for a binary decision that gives the largest decrease in that residual mean deviance. Returning to the analysis options dialog box, you'll notice that one of the options for partitioning is the minimum within node deviance to split. A node will not be split if the deviance at that node is less than the specified value. The smaller you make that number, the more complicated a tree you'll get. Once you have your initial tree, you can then simplify it doing something called pruning. Pruning means removing leaves until you get down to a tree with the number of leaves specified. Now you can remove leaves, you can prune the tree in two different ways. If you select here the radio button's specified number of leaves, it will start removing leaves based upon that residual mean deviance. If you select cross-validate, it'll select a tree with the desired number of leaves based upon how well that tree can classify each one of the observations in the dataset. The rows that are used to determine which decisions are included in the decision tree are called the training set. You can use all the rows to determine that tree if you like. You could also use the first half of the rows to determine the tree and use the second half to validate how well that tree functions. You can also use something other than the first half, perhaps the first 2/3. If you select anything other than all the rows, it'll give you a classification table both for the training set and for the rows that were withheld. Finally, there are a couple options that control the appearance of the tree plot created by R. Once you've selected the options, you can then pick the tables and graphs you'd like displayed in Statgraphics 18. I'll show you several of these after we fit the tree. When you press OK, Statgraphics will create a script which it will send together with your data to R. The tree package will build the tree, send the information back to Statgraphics, which will then display it in an analysis window. Now let's see it in action. I've loaded the wine data into the Statgraphics 18 datasheet. To run the procedure, I'll go to R Interface, Classification and Regression Trees. The dependent variable is class. The quantitative factors are the other 13 columns. When it shows me the Analysis Options dialog box, I'll leave most of the defaults alone. I will change, however, the minimum within node deviance so that I don't get too complicated a tree. I'll then press OK. On the list of tables and graphs, I'll ask for an analysis summary, the R tree diagram, node probabilities, and a classification table. For the graphs, I'll ask for a tree diagram, both the 2- and 3-dimensional scatter plots, and also a deviance plot. It's now having R do the analysis, and it's displayed the results. The tree itself is rendered in two different places. Here is the plot that was actually created in R. It's the one we've been looking at before. Over here is that same tree redrawn by Statgraphics. Since it's a Statgraphics plot, you can use graphics options here to change line types, line colors, font sizes, and so forth after the fact. Of considerable importance in judging how good your tree is the classification table in the bottom left. This takes each of the observations in the data set, of which there were 178, and uses the decision tree to predict what class of wine each of those bottles belongs to. There were 59 bottles that actually belonged to class 1. Of those, 57% were correctly classified. The program correctly classified 70 of the 71 bottles that were of class 2 and all 48 bottles that belonged to class 3. Overall, 98.31% of the 178 bottles of wine were correctly classified by the tree. You'll notice that the tree ends up with 5 leaves. It first uses a decision based upon flavonoids to split the tree, and then 1, 2, 3 other splits, resulting in a total of 5 leaves. In the bottom right, you'll see something called a deviance plot. This shows how the deviance, the overall deviance of the tree, dropped each time I made a split. The original deviance of all 178 bottles was something in excess of 380. It dropped quite dramatically on the first split, quite a bit on the second split, not quite so much on the third split, and relatively little on the fourth split. Although we could consider a more complicated tree, there's not much left to explain. Let's now take a look at the scatter plots. Here you'll see a two-dimensional scatter plot, plotting the 178 bottles against alcohol and malic acid. As you can see, there is some differentiation between the classes offered by those two variables. However, they were not too selected to be used in the tree. If I push the right mouse button and select Paint Options, I can pick two that were used. The first I'm going to pick is flavonoids. The second I'll pick is color intensity. These were two variables that were used as splits in my tree. What's interesting to see is that if flavonoids is low, color intensity is the only other thing you need to know in order to determine what classification a wine belongs to. These correspond, these rectangular sections, to two leaves of my tree, which are labeled, if you look at the structure of the tree, as node 3 and node 4. If you're low on flavonoids and low on color intensity, you're going to be classified as class 2. If you're low on flavonoids and high on color intensity, you'll be classified as class 3. If you're high on flavonoids, color intensity is not sufficient, however, to determine what class you belong to. Hence, no rectangular area. Since 3 variables were used to build the tree, the three-dimensional scatter plot is interesting. This plots the data versus 3 of the variables. I'll now need to go to Paint Options and pick the 3 that were used in the tree. One was flavonoids, another was color intensity, and the third was proline. If I now press OK, you'll see that the tree is divided into various rectangular sections. Each of those sections corresponds to a terminating leaf on my tree, and you can see that it does a good job of dividing up the observations into regions in which the class is consistent. I'm now going to show you how to use the decision tree we just built to predict the class of 3 unknown bottles of wine. I've loaded information about the 13 variables we used to build that decision tree into 3 rows of my Excel spreadsheet. I'll now take that data, copy it to the clipboard, and go back to Statgraphics. Once in Statgraphics, I'll go to the data sheet, down to the bottom, and paste in the information. When I click back to the classification and regression trees window, it'll recognize that the data has changed. What it'll do, if I go to the Tables and Graphs button and ask for predictions and residuals, is add 3 additional rows to the bottom of this table. 3 rows that it knows it can't use to fit the decision tree, but for which I want predictions. The program predicts that those 3 bottles belong respectively to classes 1, 3, and 2.